Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will look at cryptography, which is the mathematics of encoding and decoding a message. So we will look specifically at the RSA method of cryptography, which is so named for the three people who invented it. Their last names begin with R, S, and A. So the idea behind RSA cryptography is we have this message that we want to encode. We want to be able to encode or change it into gibberish really easily, but we want it to be really hard to go back to our original message in case someone intercepts it. So what we need is a process that's really easy to encode the message, but really hard to decode the message. And it turns out that in mathematics, large integers can be multiplied easily, so we're going to use multiplication to encode the message, but factoring very large integers is very difficult. So we start off by choosing a large semi-prime number n. So remember, a semi-prime number is just the product of two prime numbers. So for our example, I'm going to choose the two numbers 89 and 71, multiply them together, and you have n. So if I multiply these together, I get 6319. That is our n. In reality, computers would use a much larger semi-prime than this. In fact, the values for n, they can use hundreds of digits. And I read somewhere that if you choose n with 2048 bits, which is about 617 digits in base 10, it would take a computer like 1 trillion years to crack. Now, I'm not sure if that's accurate, but what you can get from that is it takes a long time for a computer to be able to factorize a number that has hundreds and hundreds of digits. I've just chosen a number with only 4 digits, so we can do this by hand. So now we need to calculate phi n. Remember, phi is Euler's totient function. It counts how many integers less than 6319 are co-prime to it. So that might take a long time, except for the fact that we know the rule that if you have two primes p and q, phi of pq is just p minus 1 times q minus 1. So phi of n here, phi of 6319, which is our d, will just be 88 times 70, which is 6160. So now what we're going to do is get our message and convert letters to numbers. So I'm going to start with a message like attack at dawn and convert each of these different letters to numbers. So you convert them in a logical way. A is mapped to the number 01. We always use 2 digits. T is the 20th letter of the alphabet, so it's mapped to 20, and so on. So here is our set of numbers that correspond to A, T, T, A, C, K, and so on, each letter represented with a 2-digit number. So we're going to group these in blocks so that no block can have a number larger than N6319, because then we'd have to reduce modulo 6319, which will cause problems. We'll get different answers and so on. So I can group here in groups of 4. The highest group possible would be 2525, which is less than 6319. So we're going to group them in blocks of 4. So now I need to find a number co-prime to D, co-prime to 6160. So how do I do that? Well, remember that D was 88 times 70. So what I can do is find the prime factorization of D. So 88 is 11 times 2 cubed. That's its prime factorization. Prime factorization of 70 is 2 times 7 times 5. So this is the prime factorization of D. So the easiest way I could find a number co-prime to D is find a prime number that's not in this prime factorization. So for example, I'll choose the number 13. So I can be sure that will be co-prime to D. So what I need to do is take each of these blocks here and raise it to the power of 13. So I need to do 120 to the power of 13, and I need to do 2001 to the power of 13. Then I need to reduce each of those numbers modulo 6319. So here are my blocks of numbers. I need to take each raised to the power of 13 and reduce modulo 6319. So you can actually do calculations of this size on a program like Symbolab that I thoroughly recommend. So 120 to the power of 13 gives us 216. So we make sure it's a 4-digit number, put a 0 in front. So 120 to the power of 13 is equivalent to 216 mod 6319, and I do the same for all of these. So all of these new numbers put together, that becomes my ciphertext. It's just a sequence of seemingly random numbers. So if somebody intercepts this, they won't really know what to do with it. But of course, we want the message to be gibberish, but we need the intended recipient, the person for whom the message was intended, we need them to be able to turn this into a coherent message. So, how do they do that? Well, they've sort of got to reverse the process here of raising to the power of 13. So we're going to use this here, which is Euler's formula. This result says a to the power of phi of n is equivalent to 1 mod n, and that works as long as a and n are co-prime. So how does that help us here reverse raising to the power of 13? So let's say I have 120 to the power of 13, I've got 216. How do I undo raising 120 to the power of 13 modulo n, modulo 6319? Well, I know that 120 to the power of 6160, remember 6160 was d, it's phi n, I know that that must be equivalent to 1 mod n, which is 6319. So the idea is I've taken 120 and raised to the power of 13. I want to get back to 120. So if I just multiply each side of this congruence by 120, then I end up with this here. But note, it doesn't really have to be phi n. Any multiple of phi n would work. If a to the power of phi n is 1 mod n, a to the power of 2 phi n or 10 phi n would also yield 1 mod n. So what I have here is 120 to the power of 1 times 120 of some multiple of phi n. Remember, when we're multiplying bases, we add the powers. Really, I just need to raise 120 to the power of any number that is equivalent to 1 mod phi n. That's what it means here. Any multiple of phi n plus 1 is equivalent to 1 mod phi n. So what I want to do is I want to take my answer, which was 120 to the power of 13. I want to raise it to some number so that these are equal to 1 mod phi of n. So what I want to do to decrypt this, I need to find the inverse of 13 mod phi n, because then this will just give me 120. So let's calculate the inverse of 13 mod of phi n. So in this case, phi n was 6160. So to calculate the inverse of 13 mod 6160, I can use the extended Euclidean algorithm. So I start with the normal Euclidean algorithm, write the larger number, and I keep subtracting multiples of the smaller number until the remainder is less than the smaller number, and then I repeat the process. So I just get 13 equals 1 times 11 plus 2, 11 equals 5 times 2 plus 1. So how is the Euclidean algorithm here going to help? Well, remember that finding an inverse modulo n is the same as solving a Diophantine equation. So I'm essentially solving this equation, trying to find an integer x and y. I know this will have a solution because we picked it so that 13 was co-prime to 6160. So remember, this number here, if y is an integer, will always be equivalent to 0 mod 6160. So if I solve this equation and find the value of x, what I end up solving is 13x is equivalent to 1 mod 6160. And that's exactly what I want to do in order to find inverses. So to find the integers x and y that satisfy this equation, we've done the Euclidean algorithm. Now we do the extended Euclidean algorithm. So I'm going to write 1 as 13 times something plus 6160 times something. So we backtrack here. So the last line tells us that 1 is 11 minus 5 times 2. So now I'm going to replace 2 because I know it's 13 minus 11. And now I'm going to replace 11 because this line tells us that 11 is 6160 minus 473 times 13. So expanding these brackets, I get that 1 equals 6 times 6160 minus 2843 times 13. So what that means is that negative 2843 times 13 is equivalent to 1 mod d, where d is 6160. So I can easily turn this into a positive solution by adding negative 2843 to 6160 because they will be equivalent mod 6160. So negative 2843 plus 6160 is 3317. So the inverse, the multiplicative inverse of 13 mod 6160 is 3317. So I'm going to use that now to decrypt the message. So what we need to do to decrypt the message, we need to take each of these blocks and raise it to the power of 3317, then reduce modulo 6319. So 216 to the power of 3317 is too big for something like Symbolab to use, so we can break it up. So we have 216 say to the power of 10 to the power of 331. That's 216 to the power of 3,310. So I need another lot of 216 to the power of 7. So it turns out that 216 to the power of 10 is equal to 2675 modulo 6319. So now I'll calculate this modulo 6319, but that's still a little too large for something like Symbolab, so I'll rewrite it like this. So this here is 2675 to the 331 times 216 to the power of 7. So it turns out 2675 to the power of 10 is equivalent to 5796 modulo 6319. And it turns out I was, when I've reduced it here, able to put this in Symbolab, and we get back 120 mod 6319. So we're back where we started. This was our original number 120 or 0120, which was AT. So that's how you decrypt the message. So what's going on here? It turns out that N, which was 6319, and 13, what we raised the blocks to the power of, they are what we call the public key. So as the name suggests, these numbers here are public. If you say log on to a secure website, then your computer can access this public key. So the thing is, knowing the public key, though, won't allow you to decrypt the message. We needed more information to decrypt the message. We needed what's known as a private key. So in this example, the private key was the number D, which was phi n, which was 6160, and also this inverse 13 modulo 6160, which was 3317. See, the thing is, we could not decrypt this message. We could not take our ciphertext 216 and get back the original numbers, 01, which corresponds to A, and 20, which corresponds to T. We couldn't do that without knowing D here, 6160. We can't know the inverse of 13 modulo sum k if we don't know what the value of k is. And so this is where what I was talking about multiplying and factoring comes in. See, all of this handwork here, it turns out computers can do that pretty efficiently. What computers still struggle with, or what takes them a long time, is if they have a number like n factoring it. We couldn't know what d was, what phi n was, without being able to factorize 6319. So factoring 6319 would be an easy job for any computer. But as I said, computers, they use semi-primes for n that are hundreds of digits long, and they take way too long for a computer to factor. Even if you were able to hack it, your time's probably up. You might use this secure RSA system when logging onto internet banking. You're probably going to be on that banking for like an hour at most. And so if someone tried to hack it, it's going to take way longer than an hour for them to factorize this integer. Once they factorize the integer, yes, you could hack it pretty easily, but getting from here to here is pretty tough. So that's why this number needs to be kept private, and that's why this system works. Having a huge semi-prime number like this and factoring it is hard. So it's hard to find the value of phi n, and without phi n, we can't find this inverse number here. We don't know, without 3317, we don't know to what power I need to raise my ciphertext to get back the original text. Alright, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.